Okay, guys. So,
Johnny, that was bad.
all right. So today we need to talk about exactly what we just sort of were stumbling on, which is this: what if the force isn't constant? How do we find the work? Okay. So we're going to approach this two different ways. It's going to involve a little bit of calculus. It'll be, I think, fairly basic. There is some integrals, but it's very simple integrals, I think. And then I want to make sure that you're making the connection between calculus and what the graphs mean. Okay? So that's kind of the deal for today. All right? All right, so this is just kind of the setup. All right? So remember, for a given axis, okay, so like suppose we're just talking about the x-axis. Okay? So it turns out that the work done sort of on that axis is equal to the net force along that I shouldn't say net force, just the force that's acting along that axis times the displacement along that axis. All right? You're okay? That's fine. Wait. All right, so you guys, in English, look, if you're pushing to the right and the object is moving to the right, then work is force times distance, right? Okay, so this equation here is just sort of assuming that everything's simple, that all of your motion and forces are in one line. Followed? Okay. All right. So that equation works, again, if the force is constant. That's what we just were stumbling on from that spring problem a minute ago. All right? So what I want to do here is I want to start with an example where the force is constant, and then do an example where the force is not constant. And we're going to start with gravity and springs, because those are the two forces we just talked about. One of them was constant, one of them wasn't, right? And so how do we deal with that? All right, so in the case of gravity, your force of gravity is just negative mg, right? So that's constant, yes? Okay, so if you want to find the work done by gravity, you just take whatever that force of gravity is and multiply it by your vertical displacement, right? Because gravity pulls vertically, so I'd be interested in my vertical displacement. Follow? All right, so what if we graph our force of gravity as a function of our vertical position or our vertical displacement? Okay, let's see what that looks like. And it's going to be a little bit silly, which is part of the point here. Okay, cool. I left myself a space. All right, so oops. Okay, so I could give you a mass, but it's not really important. Do you guys want numbers, or can I talk abstract?
Let's do it.
Is abstract okay? All right. So here's a pen. Do you guys agree gravity's pulling it down?
Yep.
Okay. Everybody look. You gotta watch, or you're gonna be confused, right? Everybody agrees. Force of gravity's pulling it down, right? Gravity's still pulling it down. Did the force of gravity change? No. Now is the force of gravity different? No. So my force of gravity is just negative mg, right? And no matter what my vertical position is, my force of gravity is the same thing, right? Make sense? So here's 0, I guess, right? Okay? And I'm mad that I put a triangle here. Let's just call this y. Sorry if that messed you up. Everybody good?
Yeah.
All right, now, let's suppose that I take my object that has mass m, and I move it from, I don't know, some initial vertical position to some final vertical position. Okay, so do you guys agree then that the work done by gravity here would be negative mg times y final minus y initial? Right, because this is the force of gravity, and this is my change in vertical position, right? Follow? Okay, well, let's see. Negative mg is this. y final minus y initial is this. Isn't that just the area under the curve?
It's not a curve.
It's just a curve that happens to be straight, but yes. All right? All right. So, here, and always, the work is equal to the area under, and I'm going to put under in little air quotes. Although I guess they're not air quotes, they're actual smartboard quotes. Why did I put them in the little quotes there, you guys? Sure, we got to do.
Because it's actually the area between the curve and the x-axis.
Very good, yeah. All right, so I'm going to start doing that, you guys. I'm just going to say area under the curve, and every time I say that, I mean the area between the curve and the horizontal axis. Follow? All right, now notice this notation. I don't want you guys to think this is f of x in the generic math sense of f of x. Okay? This is f for force as a function of x position. Right? Because that's what we graphed here. Our vertical axis was the force of gravity. Our horizontal axis was position. It happened to be y instead of x, but it's still position. Cool? So if you're going to look at this later and not know what this means, you might write the force as a function of position curve. Follow? All right, so any questions with that? All right, now, what if the force is not constant? Well, in the case of a spring, the force is not constant, right? Force is negative kx, right? All right, so because the force isn't constant, when we can't just do that. So let's see what that graph would look like now. So, did I give myself a blank page? I did. Cool. All right. So x for position, we'll call that in meters. All right. And here's the force of the spring. So remember, force of the spring is negative k times x, right? So isn't k, if I give you y equals mx, m is the slope, right? Now m is the opposite of the slope, right? So here it's just going to be a straight line that slopes down with a slope of negative k, right? That's supposed to be a straight line if it doesn't look like one. Good. Any problems? All right, so let's do this. For simplicity, let's call this x initial, and let's call this x final. And let's calculate the work done by the spring. Well, based on what we just learned, the work done by the spring is area under the curve, right? So let's see. So this force right here is going to be negative k times x final, right? And this one is 0, right? Good? So area of a rectangle is 1/2 base times height, right? So area,
Of a rectangle.
did I say rectangle? Sorry, area of a triangle, because we're looking for this area, right?
Yep.
So that should be 1/2 base times height. So our base is just x final minus 0, right? Because of where I put my x initial. So that's base times height, which is negative k times x final, right? And you get negative 1/2 k x final squared.
Wait a minute. Hang on.
Okay, some of you are making a realization. I want everybody to stop and ponder. There's something very important about that expression that I just wrote. So everybody think for a minute, and then I will ask Maggie why her hand is up in the air. All right, what are you going to say, Maggie? Good, that's the change in elastic potential energy, isn't it? Well, actually, it's the opposite of it, right? Which is the work done by the spring, right? Make sense? Okay, so calculating the area under the force as a force as a function of position function gives you the work done by that force. Good? All right. Now, anytime you talk about area under a curve, you should be thinking, oh, integral. Okay? So sometimes you'll be given a graph, and then you just figure out the area under the curve using geometry, right? If possible. Okay, sometimes you might need to estimate it, depends on the problem. All right? But in general, this is our expression. To calculate the work done by a force, you integrate the force as a position of function, or sorry, as a function of position. I can't talk today. You integrate the force as a function of position between your two starting and ending positions. Okay? So, in the case of a spring, let's try this and see if it works. So real quick, I know most of you in calculus have not yet gotten to integrals.
I like starting to go.
Starting them a little bit. So how should you be thinking about integrals? What are you really doing? You're undoing a derivative, right? Okay? So, in the case of a spring, let's calculate the work done by a spring. Okay? The work done by a spring is equal to the integral between our initial position and our final position of the force of the spring with respect to x. We'll pick up there tomorrow. All right, I thought we had till 15.